In this video we're going to go over the basis of differentiation. So we would usually use rise over run when we want to find the gradient of a straight line, but with a curve you can draw a tangent to it and draw a straight line through that way, but an easier way is to use differentiation, which is shown by dy over dx, and this can be used to find the gradient at any point xy. So the general rule is when you want to differentiate a function of y, so y equals some form of x, it's with respect to x, which is shown by the notation dy over dx. So you multiply the coefficient by the power, and that makes the new coefficient here, and then you reduce the power by 1, so 2 minus 1 is 1, which is why you just have x. If you do it with b times 1, b, and then x to the power of 1, if you do 1 minus 1 is 0, so x to the power of 0 is just 1, which is why there's just b. When you differentiate a constant, so a number like 5 or 7, just any number, then it disappears. So the differentiation of any constant is 0, which is why we don't have any c here. If we start with an example, a curve has the equation y equals a half x squared plus 4x minus 3. So determine the gradient at 0, minus 3 and at 2, 7. So the gradient, denoted by dy over dx, is what we need to find out first. So if we do dy over dx, remember we multiply the coefficient by the power. So 0.5 times 2 is 1. And then we reduce the power by 1. So we have 1 times x to the power of 1. So we just have x. Next one, we multiply the coefficient by the power, so 4. And then we reduce the power of x by 1. So 1 minus 1 is 0. X to the power of 0 is 1. So that's the formula for the gradient. Now it says determine the gradient at these points. So how you do that is you just plug in these values of x and it will give you the gradient. So at 0, minus 3, if you plug it in, dy over dx equals 0 plus 4. So the gradient at this point is 4. Now at 2, 7, dy over dx equals 2 plus 4, which is 6. So at this point, the gradient is 6. However, at this point, the gradient is 4. So it says find the coordinates of the point where the gradient is 0. So we have our formula for the gradient, and we just make it equal 0. Right? So we have 0 equals x plus 4. So our x coordinate is minus 4. Then it says find the coordinates, so you need the x value. The y value, sorry. So we can just plug in this value of x into our original equation to get the corresponding y value. So y equals 0.5x squared plus 4x minus 3. Oh, 1 second. So 0.5x squared plus 4x minus 3. So minus 11. So at minus 4 minus 11, the gradient is 0, i.e. the curve is flat. So we'll move on to some examples of just differentiating. So this is practicing multiplying the coefficient by the power and reducing the power by 1. So dy over dx, 4 times 3 is 12. We still have the x. 3 minus 1 is 2. So we're going to move on to the next one. Minus 5 times 2 is minus 10 x. And then 2 minus 1 is 1, so we just have the x. 2 times 1 is 2. and then x by itself reduces to 1 because it's x to the power of 0, and then, as we mentioned, the constant just disappears. So if we do them for the rest of these examples, we have dy over dx equals, it's gone, minus 20 x3 plus 1 over 5 times 5, which is 1, x to the 4. Dy over dx equals 4 times 2.7, which is 10.8, x reduced by 1, so 1.7 plus 5. 5 is a constant, so it disappears. Dy over dx, we have 5, because it's just one x, the x disappears. And then we have 8 over 15 as the coefficient, so minus 8 over 15 multiplied by minus 5 over 2, and that gets you 4 over 3, so plus 4 over 3x, and then minus 5 over 2, because it's the power, you minus 1, so it's minus 7 over 2. This next one, y equals minus 8x to the power of minus 3 over 4, so dy over dx equals minus 8 multiplied by minus 3 over 4, which gives you 6, so 6x, and then minus 3 over 4 minus 1, which is minus 7 over 4. This one, dy over dx equals, so you see how the x is on the bottom this time, we want to get it in indice form. So another way to rewrite this is 4x to the minus 1.5. One of the laws of indices is that if you have a minus in the power, then it's 1 over, and obviously if you multiply by the coefficient you get the 4. So to differentiate this, that would just be y, but dy over dx would be 4 times minus 1.5, which gives you minus 6 x, and then you minus the power by 1, so minus 2.5. So another way you might be asked in an exam is differentiation from first principles, which uses this formula. So it's more of a proof to prove that something differentiates. So I'll do an example. So we have this equation and we want to prove that its differentiated form is this, using differentiation from first principles. So we put in our equation, we have x equals lim h. So this is as h approaches 0, this is a limit. And then we have our function plus h. So wherever there's an x, you substitute x plus h. So we have x plus h squared plus x plus h, right? Because we've got x squared plus x. So we substitute our x with x plus h, which is what we've done. And then you minus the function, so minus this, minus x squared minus x, all divided by h, which is what we put there. And then if we expand this out, we still have the limit, because that's needed. We expand this out, we get x squared plus 2xh plus h squared. I've just expanded that. And then plus x plus h minus x squared minus x, which is that bit at the end. And we still have the h. So we can see here, we've got x squared minus x squared, so those two cancel. And then we have the plus x and the minus x, so those two cancel. Notice also how on the variables we've got left, they're all multiplied by h, and we have a h on the bottom, so we can cancel them out as well. So we cancel 1h, h to the power of 2 divided by h is just h, then h divided by h is 1. So a lot is cancelled, and that leaves us with 2x plus h. Now, this is important as h approaches 0, so this disappears. But we do have the 1, because h divided by h is 1. So, as h approaches 0, this goes away. So our differentiated form ends up as 2x plus 1. And that's it. So if we do another example, then it might help. So we have our formula again, and we're substituting x plus h for all of our x's. So we have 3x plus h squared plus 2, and then the formula up here, we're going to minus our original equation. So minus 3x squared plus be minus 2. And that's all over h. And we want to prove that it differentiates to 6x. So if we expand everything, we get 3x squared plus 2xh plus h squared plus 2 minus 3x squared minus 2h. We can already see that plus 2 and minus 2 cancel, so we can get rid of them. If we continue and expand this bracket fully, 3x squared plus 6xh plus 3h squared minus 3x squared all over h. 3x squared and minus 3x squared cancel, and we have h's to cancel as well, so cancel, cancel and cancel. So if we write it with what we've got left, we've got 6x plus 3h, and as h approaches 0, this term cancels, so our differentiated form is just 6x. And it's very easy to check this because, as the methods we used on the previous page, you can multiply the coefficients by the powers and reduce the power by 1, and of course constants disappear. So 3 times 2, 6, 6x, 2 minus 1 is 1, so you just get 6x. And that's it.